Hello everyone. So today we will be starting with our initiative of Edstem webinars. So wherein our first webinar would be conducted by Aditya Arora. Aditya is a Microsoft certified data engineer based in Delhi. He specializes in analytics, data warehousing, and reporting. And he would be taking the session today and will guide you through how to build a warehouse from scratch. Aditya, you can take over.
Yep. Thanks for the introduction. So, hello everyone. Probably most of you are seeing my face for the first time. I'm quite new to the organization, and as Sharat said, I'm from Delhi. So, quite far away from most of you guys are located, but good to connect with everyone digitally, anyways. So, let's talk about the webinar. The aim is to expose you guys to some engineering concepts which people like me or your fellow colleagues have been exposed to during their experiences elsewhere, right? And today we're going to talk about data. So out of that vast field of data, the topic that we have chosen is data warehousing, and how do you build it from scratch. So this is going to be our agenda. First, to understand data warehousing, and by the end of the session, understand the fundamentals which are behind building a data warehouse when you do it from scratch. And lastly, gain enough confidence that you can implement those fundamentals when the time comes. Now, I see there are around 50 people, more or less, and I believe many of you would have come with certain kind of expectations to the session, and some of you might have come with other kind of expectations. But I hope this agenda sort of gives you an idea what to expect from the next 45 minutes or so. So our goal is going to be talking about concepts and fundamentals, not the implementations, not the tools, because that's beyond the scope of a single hour session. All right. And just a few notes before I start. At the end of every topic, I will pause and ask you if you guys have any questions, and then you can raise your hand or you can unmute yourself and ask them. If you want to don't ask them in the middle, you can put them in the chat, and then at the end, we'll just go through them one by one. Okay. And if I ask you, should I move forward, just give me a thumbs up so that I can see and I will move ahead. All right. So let's just try now. Should I move ahead? Give me a thumbs up. Okay, I see a few. That means we can move ahead. So now to the real deal. What is a data warehouse? Well, to understand data warehouse, you need to in fact understand what is data engineering. Now, many people have their own definitions of data engineering, and almost all of them are correct. I like this one from a really wise guy. So data engineering is all about movement, manipulation, and management of data. That's basically it. Once you deep dive into movement, into manipulation, into management, you'll find 1,000 topics in there, but that's the essence of it. And a data warehouse is basically a place where you store that prepared data. So you move it, you manipulate it, and then you manage it within a data warehouse. So that's a typical definition, and that's basically it. If you understand these two lines, you don't need to understand anything else with respect to data warehousing itself or what it is. Then let's see. I said that tools and implementation is beyond the scope of 1 hour session. It's partly because of this image. So what you see on screen right now, I'm not going to zoom in. That's just the data and AI roadmap for 2024. So you can see infrastructure, so many tools available. Analytics, a whole bunch. ML, AI, whole bunch. Enterprise software, you've got APIs, you've got open source infrastructure. The list never ends. There's probably over 100 different tools mentioned on this image right now. So worrying about, what tool should I learn, or what cloud provider should I go with, that's not the fundamental that I personally follow. And also the reason why I have specifically excluded any hands-on or any kind of tool exposure as part of this first webinar. So if you understand the concepts, if you understand the fundamentals, then doesn't matter, you can adapt because the technology changes every 2 years. And some of you whom I've talked with before, you would have heard me saying that it definitely changes over 2 years. And a typical example is Microsoft. So for the past 10 years, they've been boasting about Azure, right? Using data services built on Azure. You've got Synapse, you've got ADF, you've got something else, and so on. And for the last 2 years, they have now been pushing a new software called Fabric, right? So this is just an example that big players are going to play their game. The technology is going to change. The tools are going to change. The fundamentals remain the same. And that's what our goal is, to understand the fundamentals with respect to a small topic that is data warehousing, right? So now we know what data warehousing is, and now we know the scope of, how much it can extend. So let's see what defines a data warehouse. So now the real definitions start. You had the fundamental definition. This is the detailed stuff. Not so much detailed, I would still say. But these are just some points which I believe are the most important. I can list down 10 more apart from this, which define a data warehouse, but these are the most important ones. So if you guys have been exposed to this domain, then you would have your own points. And probably if you want, you can put it in the chat as feedback to me even, right? But let's talk about these five first. So data warehousing, it's a central repository. That's key. So you can have a platform with a bunch of data sources and so on. But if it's fragmented, then you can't call it a data warehouse. It's just a bunch of data sources. So being a central repository with central governance is very key to defining a data warehouse, right? Then it is optimized for read. So point number two and point number four are closely related. Why it's optimized for read and why it's schema oriented? Well, data warehouse, let's call it a sibling. It has a sibling called data lake, which is optimized for write, and it's usually not schema oriented, right? So optimized for read means it's very efficient for analytics, right? It's efficient for business users coming in and running bad queries. And it's also efficient for consumption on different kind of downstream systems. Maybe there's a Click or a Power BI team downstream which wants to consume your data and build beautiful dashboards. Or maybe there's a ML or AI team who wants to consume some cleaned up data, transform data for their trend analysis and so on. So it's optimized for read. And because it's schema oriented, it's not optimized for write. Because if you're writing to a schema, then it's going to take time. If you're just dumping data, let's say in a JSON file or maybe as images or text, then it's simpler. But then when you go to read it, it's more complex. So that's those 2 points are together and they also define a data warehouse. It's schema oriented, and because it's schema oriented, it is optimized for read. Then it maintains history, a lot of it. So you see, there's no industry definition of a minimum size for something to be qualified as a data warehouse. You can have a data warehouse which is all in all 1 GB, or you can have 1 petabytes. So enterprises define this limit. For example, if I'm working somewhere, they define 10 terabytes for something to be qualified as a data warehouse. Somewhere else, it might be 500 GB. Somewhere else, it might be even more than 10 TB, right? But point is, it maintains history. It can be 3 years, 10 years, 3 months, whatever it is. But that's also a prime purpose of a data warehouse. So it's not only transaction comes and goes, it's also stored. Then the last most important point, that is batch processing. So you've got real-time processing, you've got batch processing, but data warehouse is mostly batch processing. So your typical ELT kind of systems, kind of processes, that's what constitute a data warehouse. Of course, if you have any real-time processes in there, that doesn't mean your data warehouse is no longer a data warehouse. Exceptions can be there, but mostly it's in batch mode. Okay. So that's what defines a data warehouse. Now I'm going to take a pause if you guys have any questions. If not, just give me a thumbs up. If I see 5, 7 thumbs up, then we move ahead.
So if you guys have any questions, just just let me know. I can unmute you.
Okay, maybe 5, 7 seconds more, then we move. All right. So I said we were into the real deal, but truly this is the real deal. How do we build one? And at the start, I said we are here to understand concepts and be confident enough to build one when the time comes. So you can treat this also as a cookbook, right? So if you get into a project, internal client doesn't matter. But if you are getting into a project where you have to build a data warehouse, big, small, doesn't matter. But you can treat the next series of slides as a cookbook, which you can use to, answer your questions or take off points, just like a checklist. Okay. So these are some of the things, well, they constitute most of it, but I would still say some of the things you need to build a data warehouse. You need to ask the fundamental questions. Very important. You need to find the numbers involved. Then you need to design an architecture. And this is in bold because that's very, very important. I've seen, engineers of my little experience and sometimes even senior engineers making the mistake of getting a problem statement and just start writing code, and that more often than not ends up in trouble. So you need to define what you need to do, you need to design it, you need to build diagrams, you need to write it down on paper before you get to the first line of code. So that's the most important thing, because if that's done, I would say 75% of your job is done. Implementation, now with the modern systems, modern tools, it has become so easy. You just click on something and you get a virtual machine. You just click on something, you get something installed on a serverless infrastructure. Just an example, right? So answering those fundamental questions, designing your data warehouse for scalability, for fault tolerance, and so on is 75% of the job. And then you've got deployment routines. Sometimes it's the job of a data engineer or whoever is designing the warehouse. Sometimes you have separate teams like a bunch of DevOps engineers and release managers and so on, who's going to manage this. But then, of course, you need your timelines and roadmaps valid for all projects, not specific to this one. Then the execution, again, valid for all projects. Maintenance on operations, valid for all projects, a little more for data related projects. Because if something gets messed up, it flows really quickly to all subsystems. So for example, if you have a 7 layer architecture, hypothetically, let's say, and if you have a data quality issue in your first layer and you don't notice it for 2 days, it's going to go and spread like a virus on all the layers. Then it becomes 100 times more difficult to clean it up. So maintenance and operations is also important. You need observability and you need governance to make sure that whatever you're designing is good enough and it will work. So let's get into the fundamental stuff. Now, again, like the key points which define a data warehouse, this is also my personal opinion and based on my experience of designing all this stuff, right? So these are some questions which I have always asked. And again, if you guys have been working with this kind of technology, you might have a different set of questions. But this again is like a checklist which everyone can use. So fundamental questions, what are the key technical objectives? That's very important, probably in all projects, but you need to understand what's the goal of your data warehouse. Because you see, if the goal is a bunch of business users trying to run good queries, bad queries, then your design has to be different. If the goal is to integrate it with 20 downstream systems, then your design is going to be different. If your goal is maybe just compliance, to give you an example, in European countries, you have GDPR, which is like a protocol for data security and so on. There, there's also compliance rule that you have to maintain history. So sometimes those companies, they build data warehouse just to store data, just to transform it and store it forever for compliance needs. So if that's the expected output, then your design is going to be different because then you're going to be optimizing for storage instead of, maybe bad queries. So you need to understand the key technical objectives that's going to influence your design when you're building a data warehouse, especially when you're building it from scratch. Then delivery time period valid for all projects. Again, more so for data projects as well, because you have data sources who are producing data and it grows by the day. So it becomes tougher to manage if you are, trying to load all that maybe 3 months down the line compared to 3 years down the line. Then, what kind of external systems are involved? Again, a key decision making point in deciding the kind of tools you're using, deciding the kind of networking that you're going to be doing. For example, if you have a lot of on-prem sources or targets, basically external systems, then you might need different kind of networking. You might need, if you're on Azure, just to give you an example, you might need Express Route, right? If you are working on cloud to cloud, then you might need VNet pairing, or AWS, it's called VPC pairing, but doesn't matter. All these things, they vary in names according to different tools that you're working on, but you need the answers anyways, because that's going to influence your architecture. Then the nature of data, like I said, data warehouse is schema oriented. So you need to make sure that whatever data you're going to be dealing with, it's going to be structured. There can be some semi or unstructured data, but mostly not, right? So if there's a significant amount of semi-structured data or unstructured data, then you might need to rethink and go by, data lake fundamentals, which are quite different from this. Security compliance needs important as well. Again, enterprises have separate security teams more often than not. But as an engineer, as someone who's building the data warehouse, although it's not your direct responsibility, but in my experience, who are we kidding? It is your responsibility as well. So take that same example, GDPR. There's also a guideline saying you can't have non-masked or unmasked PII data in your databases. You need to mask it. So the security team might just come and tell you this requirement, but you are the one who's going to implement it. And then, of course, that is going to impact your architecture. What kind of collation set you're going to use on your databases? That's probably influenced by some part of a security discussion as well. So that's also a fundamental question you need to ask and you need the answers for. Then the automation monitoring logging, again, it's usually after deployment, it becomes more and more important. But during your testing phase as well, if something goes wrong, you need the right kind of monitoring and logging to make sure that you solve the problem. Then it is the last point, which I think again valid for almost all kind of projects, not just data projects. If you're going into something and building something, there might be some platform preferences. You know, your client or whoever you're working for might have some tie-ups with some kind of vendors, and they might want to use the software provided by those vendors, right? So these are some of the fundamental questions that I usually ask, and I just list them down because they help me design stuff. Then with those questions comes the fundamental challenges as well. Now you can figure it out yourself if you want, or you can ask them if there's someone available to answer. So volume velocity, you need to get an idea what you're dealing with. I'm not specifically talking about the numbers you're dealing with, but a range, right? Whether you're dealing with big data or whether it's just a few hundred GBs or whether it's really small. Because again, that's going to impact your design. If you're dealing with huge kind of data, then you might need to go with a very efficient distributed system for your data warehouse. If you're dealing with something small, maybe a software installed on a VM might not hurt, right? But you need to get the answer for that. That's very fundamental. Then data quality, of course, very important. Your designs are influenced by this because whatever you're bringing into your data warehouse, you need to make sure it's of the highest quality. If it already is, then your design becomes simple. If it's not, then you need to design something additional for it. But you need to know first. So that also becomes very fundamental. Then real-time insights, not a forte of data warehousing, but you still need answers on whether the expectation is to refresh data once a day, maybe once an hour, maybe 3 times a day, maybe even 10 minutes, because that is also eventually going to impact your design. And data silos, I didn't want to add it, but in my experience, this is what I've struggled with personally the most. So you've got good data sources with top quality data, but it's fragmented. For example, MDMs, which is like your organizational data, let's say it's in some different kind of data store, and where you're going to combine this for your aggregations, that transactional data is somewhere else. They have same columns, they have everything which is matching, but there are different lengths. Why? Because both of them are in different silos, right? So these are just cool terms, but it's very common understanding when you start designing these kind of systems. So don't be bothered by the cool terms. It's very straightforward. So you need to understand whether there are silos created in your data sources and how you're going to manage them. Because, of course, it's going to impact your overall journey with designing this warehouse, right? So these are the fundamental questions. These are the fundamental challenges. Anything you guys have before we move ahead? I'm going to give you 20 seconds or something. If not, then just thumbs up again.
Guys,
Okay.
if you have any questions, just raise your hand. I'll unmute you so that you can ask whatever you want to. So whatever doubts you have or any, even though if it is a very silly question that you have in your mind, please fire away. Aditya will be able to help you out with that.
That's a very nice point Sharad mentioned. Silly questions are often the most important ones. So ask away if you have any. Well, if not, at least give me a thumbs up and then I'll move ahead. Okay. All right. Let's move. So the numbers involved, right? That's a big deal. That's the most time consuming stuff. That's the stuff which requires a lot of regression because you might, calculate something and then you get to your designing part, but then you learn that you calculated something wrong or there's something you missed. So you need to be really, really thorough in this part when you're designing a data warehouse. You need to have the right numbers or at least the right expectations with those numbers. Okay. And again, there might be some other stuff which some of you or some other people they have their own opinions on, some other requirements, some other numbers which are more important than these ones mentioned here. But this is just based on my experience. So you need to understand the number of environments involved. Usually it's just three: dev test QA, sorry, dev QA prod, or you can call it dev test prod. But sometimes you might also need sandbox environments and so on. So that kind of stuff you need to know. Number of data sources, very, very important. If you are just connecting with a single DB2 source versus 10 different sources where you're connecting with Snowflake, Salesforce, I don't know, Postgres, Oracle, whatnot, then it becomes really complex, right? And then it impacts your design as well. Then the number of tables or data objects. Why I write data objects? Because as I said, there can be exceptions where you might not be using tables, you might be using some kind of files as inputs and so on, right? So number of data objects that are emerging from each source, that's also important to understand. And of course, the number of data objects that you're going to generate, that's also important. So after aggregations, mostly the data objects numbers go down. Maybe you consume from 100 and then you aggregate and you create 10. That's what usually happens. But you need to know the numbers. Then the volume of data and its expected growth. That's the data velocity and volume part, which also we discussed in the fundamental section. But now it's about real numbers, how many terabytes or how many GBs or who knows, petabytes that you're dealing with. And then what is the rate of growth? Because this is also a mistake that some people make where they do their calculation based on what their initial input might be. Maybe they have to deal with 100 GB and then they procure 150 GB of storage thinking they have a 50 GB buffer. But then it grows at a rate of 20% per month. And then everything blows up at the end of the third month, right? So you need to know the growth rate as well, or expected growth rate. Then also, if you deep dive, then need to know your peak periods, you need to know your slow periods, and so on. To give you an example, the industry that I work in, they have their peak period during the holidays. That's around Christmas and Easter and so on. But in the middle of the summer, it's dead. The volumes go down by 80%. So that is the kind of stuff you need to know in order to design and probably save cost for your client as well. Then latency requirements, important. Whether you run your processes once a day, once a week, once an hour, once every 10 minutes, that kind of stuff you need to know. And you need to get exact numbers for it because that's going to impact your compute calculations as well. Then retention requirements. Like I said, data warehouse, one of its fundamental purpose is to maintain history. And retention basically means how much history you're going to maintain and actually how as well. So again, an example, you might need to store 10 years of history for your compliance needs or whatever. But for your analytical use case, maybe only 2 years is actively used. So you get into concepts like hot, cold storage. Hot storage is basically when your data is readily available, and cold storage is it's stored somewhere else. If you want to access it, you need to bring it down to your hot storage and so on. It's just about efficiency and cost saving. Of course, cold storage will be cheaper because it's not easily accessible or it's not fast. So all of this comes into retention requirements, and your numbers are going to define how much compute, how much storage, what kind of design you're going to build. Now, a lot of it might seem like, typical SD or backend stuff, not backend, but typical SD stuff or DBA stuff. But that's what data engineering has evolved into in the past years, at least since I've been working. You need to be full stack, and you need to know these numbers. Maybe you get someone else to implement the infrastructure for you, but you need to calculate these numbers because you are the owner of that data within that data warehouse, right? So let's take a quick example. Uh, Although there are 6 points here, but the example I've taken is just for one of them. And you see, there are 100 tables in this scenario, 30 transaction tables, 10 log tables, and rest of them are dimension tables, right? So the transaction table is approximately 1 TB in initial size. Log table is 500 GB. Dimension tables are usually small, so they are just 2 GB, right? And like I said, growth is important. So it grows 30% annually. And it says 10% is kept in hot storage, rest in cold. Then it also has some information about how much data is refreshed daily and so on. Refreshed means basically new data plus the updates you receive, right? But let's do the calculations. If we got this scenario as a problem statement, when building a data warehouse, what would we do to calculate our storage requirements? So you've got your transaction tables, which turn out to be 30 terabytes because there are 30 tables. Log tables come out to be 5 terabytes, and then dimensional come out to be 0.12 terabytes, right? So total initial storage becomes 35.12. That's what you would calculate. Seems easy enough, but it would be absolutely foolish if you just go ahead and procure 50 terabytes. It's going to blow up. So we see year by year growth. At the start of the first year, it's 35. At the start of the second year, growth at 30%, it becomes 45. At the start of the third year, it becomes nearly 60 terabytes of data. And if you're designing something for an enterprise, you think long term. So you can't think that I have a project for 6 months. I just need to design it so that it lasts probably a year. You need to think about probably the next five, right? Of course, it will also be foolish if you procure the storage at the start for the next 5 years. So you need to scale up during those times. But this gives you an idea that after 24 months, you're going to almost double your data, right? So how much do you procure? I'm not going to answer that right now because that requires probably a day of brainstorming and recalculations and so on. But this is a good start for you guys to understand how to do it. But then after you get your number comes other questions. Again, how much do we start with? Do we start with what we have, or do we start with what we're going to have at the end of 1 year, maybe at the end of 2 years? What about disk spillover? Because you can only have so much memory. If somebody runs a bad query, that is going to spill over to your disk. So you need storage as well. Otherwise, your databases are going to explode. What about temporary tables? They're going to be processes which consume, let's say, 5 tables and create one of them after joining aggregations, filtering, whatever. But you don't want to store them permanently, those intermediate results. You want them in a temporary store, whether it's in memory, whether it's in disk. That's again a design question. But if it's in disk, then how much do you need? That also factors in. You need a percentage for your temporary storage. Then what about the backups and copies that people are going to forget? If you have 20 engineers and 100 analysts working on your enterprise data warehouse after you build it, somebody's going to forget their backup. Somebody might want to run a load where they are not sure what the output is going to be. So they take a backup of a table which is 5 terabytes, right? That's an absurd assumption, but let's take it for the sake of the argument. Then you have a 5 terabyte backup in your system, and let's say their process got successful, so they forgot about their backup or the copy that they took. So that 5 terabyte is going to stay in your system. So you need some buffer for that kind of scenario as well. When it's a 2% team and 10 analysts, the story is different. When it's a 10% team and 100 analysts, story is different. When it's 1,000 people, 1,000 business users, including all downstream systems, the story is entirely different. Enterprises, they actually have special routines to clean up these backups and so on. But you need the storage anyways, right? So this is what goes into deciding what kind of storage requirements you actually have. Because whatever you get on paper, that's not the end of it. You need to do your calculations, you need to take your buffers, you need to assign some additional buffers for something which is unavoidable, something like temporary tables, something like this spillover. Maybe you need a 20% buffer for all of this, maybe a 10% buffer for people making mistakes. So this is what goes into deciding the numbers. This is just for storage. Similar way, you would do your calculations for your compute requirements, right? Then your latency, your retention, all of that comes in. In this one, maybe the retention is 3 months, so your data gets rolled off, right? Then you might not need as much of storage as it looks right now on your screen. So all of that decision making, like I said at the start, that's 75% of your job, right? Any questions in numbers? Just raise your hand. You'll be unmuted. Otherwise, give a thumbs up.
I think there is a question in the chat section.
Okay. Can't we have a view for that purpose? Which purpose would that be? You can unmute yourself, or Sharad can unmute you.
Um, Hello.
Sharad, can you unmute?
Yeah, I
Yeah,
have
so I'm
unmuted
in
you.
here. So you guys, you was talking about joining the uh, tables, and like we was talking about a huge pile of data being displayed at some point. So
Hmm,
at that point, I was like, rather than having like calculating all this memory, can't we just create a view so that
hmm.
we could visualize stuffs?
Uh, well, if you're just creating a view, not a materialized view, then you're going to
Uh-huh.
increase your compute requirements. For example, if you have, let's say, your aggregation, which is rather complex, and you define a view instead of creating all these tables and storing it, in a disk. Then what's going to happen is whenever somebody is going to access that, they're going to recompute it all over again, and that's going to blow up your compute if it's complex enough. So it's a trade off. Your point is not entirely off, but it's a trade off. So sometimes you have stuff, you have aggregations, you have calculations, joins, which are not complex enough. They don't consume enough compute. So you might define a view, right? For example, in case of temporary tables within a process, you might just get away with creating views without creating actual physical temporary tables. But in case of a data warehouse, when you have huge analytical loads, you need materialized data. Materialized means you need it stored in a disk so that it's not computed every time it's queried. To give you a very example, if a piece of data which is built with some logic of aggregations and joins, it's accessed by 10 people daily, then it's going to be computed 10 times if you just have a view. So that's the overhead, and you need to think about the trade offs.
Got it. So we have a computational over. Got it. Sorry for having a vague question though,
No,
because
that's
got it.
absolutely
Because
fine.
I have a habit of like shooting in a question if something pops in my head. So yeah, thanks a
That
lot.
means you're a good engineer. But thanks for the question. I hope I answered it, and probably for everyone else as well. You got an understanding of what it was. Thumbs up if we move ahead. Right, I got 3 or 4. Good enough for me. Now, some real theory might not be interesting to you compared to the calculations, but let's talk about it anyways. So the integration, I've given a hint of it already, so I'm not gonna, divulge more time on this slide particularly. But how do you connect to stuff? For example, if you had a DB2 connection, let's say if you have a SQL Server connection, you might need ODBC drivers or JDBC drivers, right? If you are connecting to, I don't know, something else like a Salesforce API, then you need to have that kind of HTTP procedures or integrations in your system. Sometimes you have MQs as well, which are message queues. Not very common in a data warehouse, but you can have MQs. IBM has their own, you know, tools like Kafka and so on. They basically work on the principles of MQs. Sometimes you've got users uploading manual stuff as well. So you need maybe some kind of SharePoint integration, etc., etc. So you need to understand the integration, and you need to make sure your system is basically able to seamlessly connect to all this. You don't need to go out of your way after 2 months of designing and implementation to add another component, right? Of course, you will go back to the drawing board at some point or not. That's natural. But at the start of it, you should think about all of this, and you should be confident enough that you can just blindly implement stuff without going back to the drawing board. All right. Again, you would definitely go back to the drawing board. But then centralized storage, sizing, all of that stuff we discussed in the numbers previously, right? You need your estimates, you need some decisions around what kind of storage you need. For example, if it was huge, if it had huge analytical loads, you might need distributed computing for that. That makes it way much faster. Architectures like Spark are very efficient. Hadoop is also there. That's disk based. So people are moving away from it, but just an example. Then the pipelines, real time versus batch processing. It's going to be heavily skewed towards batch because you're building a data warehouse. Then the processing itself, distributed frameworks, whether you want some auto scaling compute, that kind of stuff is also part of your designing itself. And again, some of you might disagree that this is not data, but trust me, this is what it has become into. You need to be aware of platform engineering as well if you want to be a good data engineer and if you want to design all this. So that's basically it. I'm not going to spend much time because we have, in hindsight, discussed all of this already. But let's talk about the actual data architecture just a little bit. Okay. So, first of all, I believe most of you would be aware. about classification of data, whether your data is dimensional in nature, whether it's fact is basically transactional data, whether it's some kind of logging and stuff like that. So based on that, you design your models. So the data models, stuff that you probably read in 11th or 12th standard. I read it as well, ER diagrams and so on. That's the kind of stuff which goes into this. Okay. So data modeling, basically. Now, how many layers do you need? Typically, you have a staging layer where you put your data consumed from your data sources. You have your primary layer where you do your cleaning and little bit of transformations to make it presentable. Not really presented though. And then you have a business layer where you do your calculations and aggregations so that people just can come in and consume your data on the fly. So that's actually your presentation, right? But some people they might want to consume your primary data as well. Maybe ML AI engineers, they don't want your cleaned up and aggregated data. Maybe they want to do trend analysis on a rather raw form of it, right? So deciding the layers you want, that's part of your architecture. Sometimes people even have six. They have ETL 1 to 6. They define it some other words in their own enterprise terminology. ETL 6 might be export, just an example. Then data refreshing. CDC is a very cool term, but a very important term, change data capture. So it's very fundamental to how stuff is designed in data platforms. Imagine you have a data source which is initially having 20 terabytes and it publishes maybe 1 GB per day afterwards. Now, if you were not implementing a system which is based on the fundamentals of CDC, you would probably consume 10 terabytes plus 1 GB every day. And then it grows by 1 GB, of course. But CDC basically says you only consume what has changed. There are different kind of techniques. You have watermarking, you have polling, five others that you I can think of. But you need to understand what kind of CDC techniques you need. For dimensional data, maybe you refresh them every day. Nobody cares. It's small enough. For transactions, what kind of CDC you need, right? What kind of initial node strategies you need. So that kind of stuff comes in data refresh, which you need to understand in order to implement, right? Then the data flow itself, what runs after what, how you're going to do your orchestration, whether it's what kind of dependencies you need. Some tools, they do not have event triggers, although most of them now have it. But some, they like ADF as an example, it didn't used to have it. And I'm not updated on the latest stuff. It might still not have it. But anyways, point is that also affects your decisions on your design and your tool selection as well. Because if you want interdependencies, then you need to choose a tool and you need to choose a process which can accommodate that. Okay. So layering comes first, then how you refresh between those layers comes second, and data flow is always there because if you're creating the layers, you are also defining those dependencies as well. Any questions in this? Again, 10 seconds, 15 seconds. If not, give me a thumbs up. All right. Okay, so the end of it. What else? A lot. So, like I said, my goal was to make you guys confident enough, or at least give you a cookbook to use when you are designing your own data warehouse from scratch, probably for the first time. So, what else comes into it after you have done whatever we have discussed for the last 40 minutes? Comes platform optimization, data object optimization. For example, you have created your databases, but maybe the collation is not right. You know, maybe you are joining between two tables from different databases which have different collation. That's going to cost a lot. So you need to optimize. Maybe you have analytical load, which is querying a huge table on a certain column, but you don't have an index on that column. So that query is taking a lot of time. You need to reconsider your indexing choices. That kind of stuff comes under data object optimization. right? Platform optimization, not going to talk about it. All of you are engineers. It's an endless discussion. What kind of networking, scalability, kind of machines or, deployment architectures that you want to use, all of that comes under platform. Then process optimizations, a very good point raised by Mohammad Amin here, use views. So in some process, you know, it might be wise to use views instead of materialized temporary tables. So that all comes into process optimizations. Somewhere it might be more expensive to use views. That is the kind of stuff you do in optimization. Then deployment routines, maybe your job, maybe not, but CI/CD pipelines, release processes, all that comes into deployment routines. Maintenance and operations, already talked about it. What kind of dashboarding you need, what kind of metrics you need, how long you're going to retain your logs, whether you want something as cool as Datadog or whether you just want an email alert. That's the kind of choices you're going to make. So that's what goes behind into creating a data warehouse. I will still not say that that's all that goes behind, but that's maybe 95% of what goes behind building a data warehouse. Of course, when you build it, you will grow into it. You will go back to the drawing board, add more stuff, the new ways of working for developers. But yeah, it is what it is. But this might give you a good direction at the start, at least. That's basically it from my side. Again, if you guys have any questions with respect to this topic or anything at all for the from the last 40-45 minutes, ask away.
Actually, Jerry sir has asked some of the questions. So since
Mm.
our audience is fairly new to data engineering, so he has asked some fairly basic questions so that they get a better idea about that. So if you can just switch to Q&A section, you'll be able to access that. Thank you.
Yep, I can do that. Okay, what exactly? Let's start with the first one. Difference between a database and a data warehouse. Database is basically an object store, right? Where your data objects reside. Data warehouse is a concept. It's not a physical thing like a database. Maybe a combination of databases. You can define it as a data warehouse. Like I said at the start, fragmented data sources, they are individual databases or some other kind of storage. But if you have centralized repository, centralized governance, you follow certain fundamentals, that becomes a data warehouse. All right. So it's not a physical object. Although some cloud providers like Microsoft, they like to call their tools as data warehouses. For example, Synapse, I think they call it a data warehouse. Essentially, it's not. It just is built in a way that you can, follow the fundamentals of a data warehouse. So that's the difference. Why can't we just use our regular operational databases for analytics? You can, might not be as efficient. Like I said, one of the fundamental properties of a data warehouse was it's optimized for read. So at the end, I talked about process optimization, data object optimization, indexing, collation, distribution, sharding, whatnot. All of that, might not be there in your regular operational databases. They might still be, indexes might still be there, some other stuff might still be there, but it doesn't have the flexibility and the seamlessness of modern data warehouses. So you can use it for analytics, but it's going to cost you something. It might cost you time, it might cost you compute, which essentially translates to cost. So you want to build something which is optimized according to the modern fundamentals of data warehousing, then it's going to be really nice. Okay, a related question, optimized for read. So optimized for read basically means if you're querying, then you get your result in the most efficient manner. Let me give you that same example again to explain the difference between optimized for read and write. That might explain it better. If you're dealing with something like a SQL server, right? where you have your indexes. Okay. It's a traditional database. It's already optimized in its design. Or forget about SQL Server. Let's take something modern. There's a database called Single Store, which is a distributed DBMS, right? You define your shard keys, you define your indexes, you define your keys. It automatically does, normalization for you. It doesn't allow skewness. Skewness basically means when you have certain amount of data in one node, but huge amount in another node. So it should be equally distributed. But then this is all the properties of schema orientation, right? Whereas if you go by something like a JSON or a PDF or a Word document, which is not schema oriented, it's just a dump. Imagine if you want to write a script to, dump Word files, which has a bunch of text in it. I would say it's going to be rather simple and efficient as well. But imagine you're writing a script to read from that Word file and, decode, encode, whatever, consume that data. It's not going to be that efficient. Whereas, change the scenario. If you're writing to a table where you have indexes, where you have partitioning and all that, it's going to be expensive because if you're writing 100,000 rows, those 100,000 rows are going to be distributed in, let's say, whatever number of partitions there are. That's going to take time internally. It's going to have indexes. So there's going to be index reorganization as well at some point. That's going to be expensive. But when you read it, if you're reading it on the index column, it's going to be that quick compared to a Word file. So that's what optimized for read means. Basically, you have technicalities in there, supported by databases, essentially modern databases, which allow you to read very quickly, maybe not write very quickly. And that's, a key requirement for analytical purposes. I hope I'm not going too fast, but again, if I am, just raise your hand and I can try to explain any of these questions in a different way. So, difference between structured, semi, and unstructured data. Well, structured is what we have been talking about. Schema oriented is basically structured. Not entirely. You can still call, semi-structured data as little bit schema oriented. Not really. So imagine a table, you have columns, you have rows. If you just open a table, even in an Excel, you can see the structure, right? You can go to a row, you can select a column, you get a cell. That's structured data for you. Semi-structured data is something like a JSON or an XML file where you have attributes, but it's a file. You can't just, go to cell number 29 or row number 28. You have a bunch of curly braces and then you have attributes under there. So there is still attributes, there's still metadata in there to explain what the field is, but it's not really structured. So that's what semi-structured is, and unstructured is what you're seeing on your screen right now, my video file, right? So nothing you can do to just select a data point in there unless you do a lot of processing. What types of data sources typically feed into a data warehouse? Well, a lot of types. Typically, as well, I would say a lot of types. So, data sources, I would say the most common example is other RDBMS. So, your data warehouse might be built around an RDBMS platform, right? If you're building it on, let's say, Synapse, which is heavily integrated with SQL Server. It has serverless SQL. So that's RDBMS in a sense. And then you can connect different kind of stuff. You can connect, blob storage, you can connect other SQL servers, you can connect Oracle to it, you can connect Salesforce, Snowflake, Informatica, whatnot. But typically, I would say it's RDBMS with RDBMS with different purposes. So usually transactions from a normal operational database going into a data warehouse where it's optimized for read and analytics. But it's basically a DB. Why do data warehouses need to maintain so much history? Simple answer is that's their fundamental. Where does that fundamental come from? Well, it comes from the requirements built over the years. I don't know when this concept was invented or discovered. I don't know what to call it, but I think it was in the late 70s or 80s, something by IBM. So from that point onwards till the next 40, 50 years to today, these fundamentals have evolved, right? And maintaining history has become a core feature of a data warehouse. Why it has become a core feature? Because there's requirement. I gave you an example of GDPR. GDPR, for certain kind of data, it has a requirement of maintaining at least 2 years for compliance purposes, right? So if the government comes to the enterprise and says, I need that transaction from 1.5 year ago, they need to have it. Otherwise, they're going to face consequences. So that's a typical use case of maintaining history, you know. And then you have analytics as well. And if some of you have read a cool blogs or something like I've done about ML AI trend analysis, you would know the more data you have, the better your predictions are going to be. Not true entirely, but yeah, mostly. So the more you train your data, the better model it's going to be. So that's why you might want to maintain history in a data warehouse where you can consume it from 10 for trend analysis somewhere downstream, right? Just two examples of why they maintain so much history, but simple answer is that's their fundamental built over the last 50 years or something. Schema oriented, like I said, during explaining the structured data and during explaining optimize for read, it's important because it allows you to read quickly. It allows you to query stuff, do analytics on it really, really quickly, right? So you have tables and they have been developed because there was, of course, a need for it. It's obviously easier to find a data point in an Excel compared to a Word, you know. So that's basically it. The searching functionalities, that's also faster in schema orientation. And it basically means having it in a tabular format or at least having some kind of metadata with it. If you don't have a metadata, imagine a file where you have names, right, of all the attendees of this meeting. But some attendees are presenters, some are just attending the meeting, right? But you don't have that metadata. So how will you figure out who's who? So let's make it easier. If you have a schema orientation, you might have a separate column for attendees and you might have a separate column for, presenters and so on. Just a vague example, but that's what it is. That's a use case dependent question. Do we need batch processing or can we do real time? From my experience, I'm telling you that more and more people, more and more enterprises are moving towards real time analytics and real time data processing as well, because that's cost saving. It might be, not as cost efficient while implementing or developing it. More developers are required, more resources on your platforms are required and so on. But the business value, it's huge. So the entire value chain of whatever we do as software engineers, it boils down to a point with some business decision happening on the ground to the end user, right? So real time processing aids that. For example, if I'm working in a supply chain company and I have data about, truck drivers and their locations and points and whatnot. If I'm doing analytics on that once a day, then I would know maybe this truck driver took a wrong route, which probably ended up wasting 2 hours. Maybe he should have delivered something first and then second, that kind of stuff. But if I'm doing real time analytics and I see a flag that it's going to cause a 5 hour delay, then my business user can call that truck driver and say reroute. So that's another simple example of, batch processing versus real time. It always depends on use case, but the industry trend is changing because the value chain is driving it. How is data actually moved from source systems to the warehouse? Through different methods. Uh, like I said, ODBC, JDBC, whatnot. If you're connecting to on-prem sources, you have express route and so on. These are all technicalities which are implemented by open source developers or organizations which provide them as services. So that's how it moves. There's networking behind it, there's protocols behind it. For example, You might have learned about TCP, IP at some point in your life during academic or corporate careers. But that's what goes on. There's protocols which transfer the data over the network. We don't get into those protocols as data engineers. We just define what we need to use and we just configure the connections. That's basically it. So connection is a term that you're going to use a lot when you start working with this kind of integrations. Why separate hot and cold storage? Difference I've already explained. Hot is fast, hot is closer to you. If you are someone who's querying your data source, imagine hot storage as closer to you, cold storage as far, far away, right? Why do we need it? Well, because we want to save money. So cold storage is going to be cheaper because it's not fast. It's stored somewhere in an inefficient data center. Whereas hot storage, it might be in your partially in your memory, partially in a really high speed disk, and so on, because you need to query it a lot. So if I have 10 billion rows and I only use 100,000 for my querying daily, why keep the entire time 10 million? I might keep 9.5 somewhere else in a cold storage, which is costing me maybe 10% of my hot storage cost. So that's why we need them. What happens if our initial storage estimates are wrong? Well, we go back to the drawing board. Fortunately for us and for our generation who are working today, the cloud providers, if you're working on a cloud system, they've made it really easy to scale up and scale down. So if you made a mistake and probably you procured a system with maybe 1 terabyte of storage and you end up needing three, then it's not like you want to destroy your entire platform and then rebuild it again. You can do it, but scalability has become really seamless nowadays. So you can just go in and set it to 3 terabytes. It's going to have its downtime, it's going to have its impact. You might need to do some reorganization and so on, but it's relatively easier. But fundamentally, if your calculations are wrong, you need to go back to the drawing board. You need to pass some red tape as well, because in real projects you get approvals and so on. If your estimates become wrong, then you need to get those approvals again, etc., etc. How do you justify the ROI of building a data warehouse? I think I partially answered it by answering the value chain system. So whatever we do as software engineers, like I said, it's part of a value chain where the end goal is impacting some end user and driving business value. So data warehouse is same. You want to do analytics to find out insights that you don't usually see out of the box. You might think that your sales are going very well, but maybe they're not. Maybe they are just focused or skewed towards one region. That's the kind of thing you will figure out when you create a data warehouse and do analytics. Who are the typical users of a data warehouse? A term that I've been using a lot. That's business users and downstream systems, which again have business users. So you can have some kind of business users who are domain experts, like I said, sales or supply chain, or route optimization. Take something else like HR even. These are the kind of people who use your data, and that's why you do all this transformation and manipulation of the data to make it easier for them to understand. That's why you create these beautiful dashboards so that they just sit on the screen and make a really important business decision based on whatever input you provided them. So yeah, I would say the most typical users are business users. You can say other engineers with other downstream systems, but eventually they're also going to have business users. So I think that more or less answers all the questions. Okay, there are a couple more. What is a serverless warehouse? Uh, Physically, it's not serverless. There is infrastructure behind it, but from an end user perspective on a cloud provider, you don't need to define your limitations. You can just select serverless. And what happens is if your query or if your analytical processes use maybe 50 GB of compute, then it scales up to 50 GB. If it uses 500, it scales up to 500. If it uses 5, then it scales down to 5. That's what serverless is. So you don't maintain the actual infrastructure, you just use it blindly. And the cloud provider in the background, they manage it automatically. Difference between clustering and partitioning. Okay. Well, partitioning, well, clustering can mean different things if you are on different platforms, but fundamentally, it's how do I explain it in respect to partitioning? But let me explain partitioning first. So partitioning is basically division of your data, right? Like I said, in distributed systems, you have nodes, and those nodes have their own memories, their own storage, and so on. If you have 100 GB, you might not want to store it on a single node. If you have 10, you distribute 10 GB on each, ideally, without skew. So that's what partitioning is. And how it helps is if you're querying something, let's say you partition based on city. So you have 10 partitions based on one city each. And if your analytical use case is just, consuming data from Delhi, for example, and that's stored in a partition. So when you query for Delhi, it's not going to do reshuffling and go to other partition. It's just going to take that one and give you the result. So that's optimized, right? That's what partitioning is. Well, clustering, it can mean a lot of things, but it's very close to what partitioning is. So cluster is basically a bunch of, you know, resources. And like I said, in the partitioning example, you might have 10 nodes. So the 10 nodes can combine and create a cluster. Well, they usually do. So let me give you an example with Spark architecture. You have a driver and then you have worker nodes. So all the worker nodes and the driver, that's basically a cluster. So as an end user of that application running on Spark, you won't say that I want to, put this data in node number 10. You just run your query and the cluster handles that. They have a cluster manager in most cases, almost in all cases, and that manages this distribution, this optimization and everything. So that's what clustering is. And it's basically what partitioning is on a data object level versus the infrastructure level. I think I've answered everything, hopefully not too quickly. But if there's anything else, just raise your hand.
Yes, guys, if you have anything else or if you want him to repeat on any of the topics, Aditya would be able to help out with that. Else he can, as usual, give up a thumbs up and we can wind up.
There are more questions asked just now, if you check it.
Okay. I don't. Oh, yeah. Now they are popping up. What are the critical factors on deciding? That's a very good question. What are the critical factors deciding between a lake, a warehouse, or a lake house architecture? So first of all, lake house is again another cool term devised or at least got famous in the last year or so, probably two, which is a combination of a data warehouse and a data lake. So data lake, like I said, it's a sibling of a data warehouse. Now we know what a data warehouse is, what its purpose is. Data lake being a sibling, it has its own purpose, quite different, but yeah, more or less the fundamental purpose is same, to do analytics on stored data. But the kind of data and how they store it, how they process it is different. So data lake is mostly about semi-structured and unstructured data, and mostly about real-time processing, right? Lakehouse is a combination of both, where you have ETL, ELT kind of processes, and then you have a lot of real time as well. Like I said, even in a data warehouse, there are exceptions. So by definition, you can always call it a lakehouse. But let's say when the distribution is close to 50-50, then that's when you call it a lakehouse. Now let's talk about the application part of it. Warehouse being a typical batch mode kind of architecture, it might not be used for real-time decisions like that. For example, credit fraud. If a fraud is happening, you might want to act quickly to mitigate that threat. In that case, you might need a data lake because you have a source which is coming from Azure Event Hubs, which produce real-time data events. You're consuming it from Kafka, and then you're doing real-time analytics and sending your alerts or your whatever to your business users and your analysts, right? Who can then take that decision, business decision. So that's when a data lake comes in handy, right? In use cases like AI, I would say AI is a lot of things. Mostly now it's prompt engineering is becoming really, really famous in AI compared to trend analysis. In that case, you need models which are trained, right? They're not, at least most of the models that are available out of free, they're not reacting on the fly. They do web crawling and so on for you in pro versions and etc. But mostly there's a model which is already trained. So in that case, maybe a data warehouse is good enough. Maybe you don't need to expend those resources on creating a data lake because you just want to train that model, store it somewhere for people to use, and maybe you have a frequency of retraining it every month, every week, or maybe once a year, right? So in that case, warehouse might be a better option. And lake house, like I said, 50-50, where you have both these scenarios, you choose a lake house, but it's a rather new term, and it's just a term. It's not new. Well, it is a new concept, but not so much different from the others. It's just a combination of two. So that's where the use cases come, where there's business value in making real-time decisions. That's when you go with data lake. Where there's business value in probably looking at a report once a month to see how the trends have been, a data warehouse might be better, right? Similar use cases with AI and these. Then any major security issues that we should be aware of? Oh, well, a lot. And to be honest, I don't even know all of them. Being a data engineer, you get exposed to some of them. For example, mostly related to networking stuff. You might be connecting to a data source without realizing you're going over the internet. You just go Google stuff, find out that integration, implement it in your software, voila, it's done. You have your data. But turns out you are in a private network. Your organization is a private network, but then you're going over the internet because you exposed a port. And now hackers can come in, or stealers can come in and steal your data. You have a data breach on your hands. So that's one of the major security issues that fortunately I have not been exposed to, but I've seen, in my corporate circle, people have been exposed to that. Not frequently, but yes. So internet is your biggest threat when you're working with these kind of systems. You need to make sure your networking is solid, right? If you're in private networks and your sources are in private networks, then make sure you do private network peering, that kind of stuff. You use private tunnels, you know, endpoints, etc., etc. You don't go over the internet. So that's one security issue that I would say is quite critical. The other one, with respect to data, I would just like to give an example, is PII. So you might have exposed data which all engineers and analysts can see, but you should have hidden it because of compliance rules or data security rules here or wherever your data is located. So that's the kind of stuff which is a security issue. One which I have been practically part of is our vendor. They had their monitoring dashboard in US geography. And the client that I work for, it's in Europe geography, and GDPR being applied there means that you can't send data outside of Europe. And our vendor accidentally created a dashboard and was pulling data into the US geography, so that cost them a lot. They had to face penalties and so on, but that's a security issue. Your data shouldn't go out of the geography that it's not supposed to go out of. So these are just two, three examples of typical security issues. I don't see any other update. Anything else? I see that we are 17 minutes over time, so I think that's a good start.
Yes, definitely a good start. So uh, Thank you, Aditya, for taking this session today. And thank you all